Hello everyone, welcome to my YouTube channel Easy Way to Learn. I am Shalya Tripathi and today's topic of discussion is allotropes of carbon. So let's get started, remain focused and follow the lecture. So what is an allotrope? When an element exhibits various physical forms but chemically it is same, then we say it is an allotrope. So carbon exhibits three allotropic forms: diamond, graphite and Buckminster fullerene. See, diamond, graphite and Buckminster, all the three are chemically carbon. They are represented by C. How can we say they are chemically same? See, when these are burned in oxygen, the only product that is formed is carbon dioxide and nothing is left. So we can say that they are made up of just one element, that is carbon. See, physical nature of all the three is different. The diamond, you already know, is used as a gem. It is colorless, transparent, shows extraordinary brilliance, hardest known substance in nature. So its hardness is due to its structure. It shows tetrahedron structure where all the carbon atoms are attached to other four carbon atoms. See, this is representing carbon. So this carbon is attached to nearest four carbon atoms. Similarly, all the carbons are attached to another four carbon atoms. So this forms a giant network. And this gives rigidity or hardness to the diamond. And since all the four valence electrons are used up in forming covalent bonds, so no free electron is there, hence diamond is non-conductor of electricity. So you can add one more point here, non-conductor of electricity, non-conductor. Of electricity. Since there are no free electrons, all the four valence electrons are used up in bonding. Next is graphite. If we see the physical form, it is soft, slippery and conducts electricity. Again, these properties are explained on the basis of structure. So in the structure we see that carbon atoms are present in the form of sheet, hexagonal. See, these carbon are arranged in interlocking arrangement and they are in the form of a hexagonal ring. So we get flat sheet or flat layer of carbon atoms, then another flat layer of carbon atoms. So here in this flat layer or these parallel layers, what we see that each carbon is joined to three next carbon. See here 1, 2 and 3. Similarly, here we can see 1, 2 and 3. So fourth valence electron is free. And these two layers are joined by a force that is called van der Waals forces. It is a weak force. So the atoms are joined by, or the layers are joined by this weak force. So this weak force is holding the layers of carbon, interlocking carbon sheet. So this gives it a slippery nature because these sheets can slide over one another. When heat or energy is provided, it slides over one another. Hence it is used as a lubricant, and because it can withstand high temperature, or when the energy is given, all the energy is used up in sliding the sheets. So graphite doesn't get disrupted or destroyed, or it doesn't melt. So this is the reason for high melting point. It is near about 4000 degrees Celsius. See, so and the third valence electron is free. Fourth valence electron is free. So that helps in conduction of electricity. So it is a good conductor of electricity. Again, I'll repeat. 3 electrons are used in forming the covalent bonds in this flat sheet. And the 4th electron, valence electron, is free, and that is helping in conduction. And this kind of structure gives its slippery nature, hence it is used as a lubricant. Then another allotrope is Buckminster fullerene. One molecule of Buckminster is made up of 60 atoms of carbon. So this is the smallest allotrope. These are giant network of carbons, both diamond and graphite. But this is the smallest allotrope, since one molecule of Buckminster fullerene is made up of just 60 atoms of carbon. They are arranged in a spherical form, just like a football, having interlocking 20 hexagonal rings. See, 20 hexagonal rings and 12 pentagonal rings of interlocked carbon atoms. So these, see, this is the pentagonal ring. I have drawn just one interlocking system. This is pentagonal ring, and it is surrounded by hexagonal. See, these are hexagonal rings that is surrounding the pentagonal ring. So this repeating unit is present, made up of 60 atoms. So there will be 20 hexagonal such rings and 12 pentagonal rings. Buckminster fullerene is not very hard nor very soft, whereas diamond is hardest substance, graphite is soft, but this one is not very hard or not very soft. Next we will see versatile nature of carbon. Let's see versatile nature of carbon. See, carbon forms large number of compounds, and it is much more than the number of compounds formed by other elements. And this uniqueness of forming large number of compounds is because of two factors that we'll see in a while. The first one is catenation or self-combination. Another property or the factor is tetravalency of carbon. So let's understand catenation first. So catenation is the unique ability of carbon to join with other carbon atoms, giving rise to large molecules. That is, carbon can form large carbon chain. That is, it can attach to a chain of carbon, and this chain is stable. So it can give rise to large number of molecules. So it can form a long chain. It can also form branch chain like this. This is called branching. It is attached to one more carbon. So it can give rise to branching, or it can also give rise to ring, carbon ring. Like this one I am drawing is hexagonal ring. So this tendency of carbon to join with other atoms of carbon to give rise to large molecules is called catenation. So it can form long chain, branched chain, and also it can form ring. Okay. One more thing, carbon can also carbon forms single bond. It can also form double and triple bonds. So when carbon compounds are having just single bond, like in this case, it is having just single bond, such a compounds are called saturated compounds. Saturated. And when the carbon is linked to another carbon by a double bond, or it is linked to another carbon by a triple bond, it is called unsaturated. So these are double and triple bonds, and it represents unsaturated compounds. Unsaturated compounds. So carbon can form single bond double bond and triple bond. So this is also the definition of saturated and unsaturated compounds. So in a compound, if you are seeing just single bonds, it is saturated. If you get a double bond or a triple bond between the carbon atoms, then it is unsaturated. Okay, the property of catenation is also exhibited by silicon, but the extent of catenation is very less. So silicon forms compound with hydrogen. See, it will also form 4 bonds. So silicon will join with another silicon, and this chain can extend up to 7 to 8 atoms of silicon. Seven, 8. And these are all hydrogen atoms that are present. So silicon forms compound with the hydrogen, and this chain extends up to 7 to 8 atoms. This is because silicon compounds are more reactive than carbon compounds. So after carbon, this silicon will hold the second position for forming this or showing catenation property. So this has been asked. See, and this carbon-carbon bond is very strong. So the carbon, this bond is very strong. Next property is tetravalency of carbon. So next point is tetravalency of carbon. Or carbon can form 4 bonds. So another point is tetravalency of carbon. Tetravalency means carbon has 4 valence electron, so it can or it will form 4 covalent bonds with other carbon atom or other atom or monovalent atom. So here it is forming 4 bonds with hydrogen. So this molecule is methane, this most simplest carbon molecule. And carbon also can attach to 4 carbon. So this is because of 4 valence electrons in its outermost shell that is helping it to form 4 covalent bonds. Okay, it can also form bonds with other elements like oxygen, nitrogen, sulfur, chlorine, and the compounds that are formed are exceptionally stable. So the compounds will be exceptionally stable. See, this compound you already recognize, carbon dioxide. And the reason for stability is that carbon atom is a small atom and it can hold on to shared pair of electron very strongly. So tetravalency of carbon. So compounds, you can write compounds are very stable because carbon is a small atom or carbon is small atom. You write down carbon is a small atom and hence its nucleus can hold on to shared pair of electrons tightly. See, if carbon is forming bond with another atom which is larger in size, then the bond will be weak. Then the covalent bond will be weak. So if carbon is attached to or is combining or forming a covalent bond with another atom which is large in size. See, if carbon is this much big and the other atom that is larger in size than the carbon atom, so this bond will be weak. Reason being, the nucleus of the carbon atom will not be able to hold on to the shared pair of electron that tightly. So carbon forms a strong bond with atoms of nearly same size. So same size atom, if it is forming a covalent bond, so atoms of nearly same size, then the bond will be strong. But if carbon is forming bond with another atom of larger size, then the bond will be, covalent bond will be weak. Hope you understood the topic well. Please like, share and subscribe and enable the notification bell. Thank you so much.